All right, good morning, guys. Today we are going to be talking about geometric sequences and series. So in our workbooks, I'm on student activity sheet 3, exploring geometric sequences and series. And it is 5 pages, just 1 through 5. And if you look at the bottom, we're actually starting on page 15, and we will end on page 19 today. All right, so let's see, when were y'all here? Tuesday. So we talked about this chart on Tuesday. Remember, this was our geometric sequence. Geometric sequences go with exponential functions, okay? So they use a common ratio. And for this specific one, you can go back and look, but our common ratio ended up being 4/3, okay? So somewhere on your workbook page, I want you to write common ratio was 4/3. Okay. All right, it says, in a previous lesson, you considered the sequence of perimeters of the figures formed by dividing sides of an equilateral triangle and drawing new triangles. As you know, this sequence can be thought of as a function. What is the domain of this function and what is its range? So way back when, we learned what a domain and range were. So remember that domain is my x values. So my input values, okay? And I want you to remember that range is my y values or my output values. So figure number. Those are all going to be our x's, our domain, and our perimeter is our y, which is known as our range, okay? So on number 1a, it says, what is the domain of this function, okay? So domain is the set of positive integers 1, 2, 3, and 4. However, the range is 3, 4, 16/3, and 64/9. So make sure you have that down on A and B. Okay, you're just writing your x values for your domain and you're writing your y values for your range. Okay, C says, write the recursive definition for the function. Okay. It says, you can represent this geometric sequence using function notation. So what this tells us is when we put in a 1, we get out a 3, like it does right here, okay? Then this down here is our function notation. So 4/3 is our common ratio, okay? And you remember what I said yesterday, n minus 1 is our recursive definition. Okay, so we have to know the answer to the term before the term we're looking for. Does that make sense? Like, I have to know what figure number 1 is before I can answer figure number 2. Or I have to know what figure number 2 is before I can answer number 3. Okay? Okay. Number 2. So I am first going to read off of your workbook page. So it says, the drama club will give one performance every night except Sunday and Monday for 2 weeks, which is only 10 nights. Club members believe that revenue from the first night production will be approximately $3,500. For each night after that, they think the revenue will be 70% of the previous night's revenue. Use this information to estimate projected revenue for each of the first 5 nights of the production. Then write a function rule that models this situation. Okay? So on your notebook paper, not your notebook, your workbook. I want you to draw this chart for me. Okay? And then we are going to write first term, which is $3,500. Our common ratio is 70%. But we cannot put a percent in an equation, so we have to change that to a decimal. So remember, we put our decimal at the end and we move it 2 times. We're looking, our N is going to be 5. We're looking for the first 5 nights, okay? So our function rule, we learned this yesterday. First term. And yesterday, we added because we were doing linear. But today, we are doing exponential. So we are going to multiply by our common ratio. And since it is exponential, our recursive definition is going to go in the exponent. Okay? So I want you to draw an arrow and I want you to write exponential. All right, I'm going to click off of this. So if you plug a 2 into that equation for your N, you should get 2450. If you plug in a 3 for the N, you should get 1715. If you plug in a 4, you get 1,250 cents. If you plug in a 5, you get $840.35. All right, still on number 2. It says the table shows the revenue estimates for the first 5 nights of the production. Can you use the pattern in the table to develop a rule that approximates the revenue, which is our Y, on any night, which is our X? It may help if you add a process column to your table like the one begun here. Once you have a rule that you think will work, compare it to the one shown here, okay? X and Y, okay? That 0.7, remember, is our common ratio. So all it's doing each time is multiplying by our common ratio. And it's using N minus 1 to do that. So this page is just kind of a review, I guess, of number 2. It's just showing you another way to do it, okay? There's multiple rules that you can use, but the one that we did on, that we wrote on our paper is probably going to be the easiest one for you. All right, let's see. What's next? All right. Look closely at the revenue projections for the first 5 nights. Do you see that they form a geometric sequence with a common ratio of 7? Okay, here it is again. Hit play. It tells us that for every night, it is being multiplied with a common ratio of 0.7. It's a constant multiplier because, 1, it's a constant, same thing every time, and it's being multiplied every time. Now it's just showing you again all the revenue. The constant multiplier for the y values in this exponential function is the common ratio in the geometric sequence formed by the range values of the function. So what you need to know here is that exponential functions goes with geometric sequences, which is what we learned when you were in class on Tuesday, okay? All right. Page 5. We're still on number 2. Number 2 has a lot of parts. It says, study the geometric sequence of numbers. The vocabulary and notation for a geometric sequence are the same as with an arithmetic sequence. Each number in the sequence is called a term, and the different terms of the sequence are indicated using subscript. Okay, so for this sequence, what is T1? So, T1 is my first term. So if you look at 1, you get 3,500. Then it asks for T4. That's my fourth term. You get 1,250. Okay, so that's all that's asking. Just to find the number and define the term. All right, we're on number 3. So on number 3 on your workbook, that last sentence that says, how does the general formula compare with the function rule you found in question 2? I want you to mark that last sentence out. Okay, mark that last sentence out. All right. It says, first it shows our chart again, and it shows each y value, the range value, or the revenue, spaced out with the common ratio on top of it. And it says, just as with an arithmetic sequence, you can state a recursive definition for a geometric sequence. What is a recursive definition for Tn, the nth term in this geometric sequence? So I want you to hit check. What do you notice? It is using n minus 1. Remember yesterday when I told you anytime you see n minus 1, that's the recursive definition, okay? Same thing for today. N minus 1, is the recursive definition, okay? So on number 3, it says, write a recursive definition for the revenue from the performances. So what you're writing is this right here. All right, next part says, in the previous exploring, you learn how to write a general expression for any term in an arithmetic sequence. Can you write a general expression for any term Tn in a geometric sequence? Just as you did for the arithmetic, you use what you know about writing function rules to help you. All right, so the second part to number 3 shows a new formula. Okay, right here. We've already written that on number 2. So remember that 3,500 is our first term. 0.7 is our common ratio, and n minus 1 is our recursive definition, but it's in the exponent because this is an exponential function. Okay, so you need to make sure you have both this equation, which is our recursive formula, and you need to have this exponential function. Okay, they work the same way. Both ones are totally fine to use. All right, the next question says, how much revenue is predicted for the 10th night of the performance? So we're looking for the number 10, okay? We're looking for the 10th night. So what I'm going to do is I'm going to take this equation right here, and I'm saying T10 3,500 times 0.7, 10 minus 1. Okay, then I have to simplify. 3,500 times 0.7 to the 9th power. Okay? This equals 141.2376 and so on. Okay? But we're dealing with money. Okay? So you have to remember, when you deal with money, we only deal with 2 decimal spots. Let me back up. This is actually 2376. So, our 10th night, that's how much money we would make, our revenue. Now, I also want you, on the bottom of number 3, I want you to find the 14th night for me as well, okay? So go ahead and do that. All right. I want you to skip number 4. I want you to put an X on it in your workbook, and we will do that one. We'll talk about that in class when you come next Tuesday, okay? That one's just easier to talk about in person. There's a few different things we need to look at. Okay. All right, this goes with number 5. Okay, so go ahead and flip over to number 5. We're going to talk about this. All right, it says the drama club is interested in how much total revenue they might expect from their first 10 performances. In other words, they wish to find, and then you have this big, fancy equation. Okay, remember yesterday we talked about this. This is a sigma, which stands for sum, also known as the total. Okay, remember we had this sigma. This is n equals 1. These are our number of terms. And then here is our equation. Okay, which is what they've done right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is where the 10 comes from. This is the first term. Here is our equation. Okay, it is in exponential form because we are looking at geometric sequences. And remember, geometric and exponential go together like peanut butter and jelly. Okay? All right, so it says, in the previous exploring, you learned how to use the fact that that pairs of terms had a common sum to find the sum of a given number in an arithmetic sequence. Does this approach work for geometric sequences? What is the sum of the first term and the 10th term? Okay, so remember yesterday, if we added the first term and the last term, we got a number. If we added the second term and the next to last number, then that term equaled the sum of the first number and the last number. Remember, everything was the same. Then at the end, we counted our pairs and we multiplied that sum by the number of pairs. So what I'm going to do right now is I am going to show you for a geometric. So first term is 3,500, okay? And then the last term, the 10th term, is 141.24. Okay, so I'm adding. All right, so I get 36.41 and 24 cents. Now, it says, what is the sum of the second term and the 9th term? So here's the second, here's the 9th. So I've got 24.50, 201.77. Does this equal this? No. Okay, so it can't work because those would have to be equal in order for me to do the way we did yesterday by using pairs. So I'm going to delete this part so we can check our work. All right, so there it is. All it's showing us is the sum. Shows us this, and then it says at the bottom, do these results indicate that there is a common sum for pairs of terms of a geometric sequence like the common sum you can find for pairs in terms of an arithmetic sequence? The answer is no. It doesn't work for geometric. Okay? Only for arithmetic. So on this next page, it actually shows you what we just did, okay? So I'm going to go ahead and click okay, number 5. What is very important to write on number 5 is what I write right now, okay? This is a formula you're going to have to know. All right, this is to find the sum, okay? Or not the sum. Let me back up. Oops. The sum of however many terms you're looking for, okay? So if you look, it says you found the first sum of the 10 terms in the geometric sequence. Yes, we could go back and we could add up every single number. But we don't have time to do that. We don't like doing that. So for the arithmetic sequences, we learn the pair method, okay? Now, for geometric, there's a formula that we can use to plug in. So, N stands for number of terms. T1 is first term. R is our rate, also known as the common ratio. Okay. So next week, I will show you the easiest way to put this in your calculator. All right, so we have S of 10 because it tells us we're looking for the sum of the first 10 terms. Okay. T1, remember our first term that we did was 3,500. Okay. Next, we have 1 minus our ratio or our rate, which was 0.7. We put our N, which is 10, divided by 1 minus our rate. Okay, so I'm going to write this so you can see it. N is 10, T1 is 3,500, and R is 0.7. So as long as you know all of this information, it's really, really, really simple. Okay? All right. I can't show you my calculator on here, but I'm going to talk you through it. Okay, so if you're on your calculator, what I want you to do first is type in 3,500, a parentheses, alpha, y equals, enter to get my fraction bar. Okay, up top we are typing in 1 minus 0.7, and we're going to raise 0.7 to the 10th power. And remember, I showed you how to raise to the power. It's that arrow that's pointing up under the clear button. Okay, and you're typing in 10. Then we are hitting our down arrow to go to the bottom fraction bar, and we are typing in 1 minus 0.7. Once you get that typed in, I want you to hit the right arrow, close that parentheses, hit enter. And if you typed it in correctly, you should get $11,000, $11,337.11. Okay? So that is the money that we would make for the total of our first 10 performances. Okay? Now I'm going to click off of this. I'm going to click check, okay, and there it is. Shows you the exact thing. All right, next page, if you look at number 6, it's another one of those proofs. So this just shows you what we did in words. So I'm actually going to talk about that on Tuesday in class. So for now, I want you to put an X on number 6 in your workbook, and we will come back to it next week when you come back. I think it's Tuesday. We'll do questions over topic 1. All right. Let's see. Here's the formulas again on page 12 if you want to go back and look. These are the same thing, okay? Just worded a little different. So I think, is that the last? Yes, that is the last page. So now I'm going to swap over All right, we are on number 7. It says, use the general formula you derived in the previous problem. Find the sum for this geometric series. So this is where we are going to use the formula we just wrote down. I want you to remember that T1 is the first term. R is the rate. And N is the number of terms. Okay, so if you look, our first term, the first number you see is 256. Okay. Now, our rate. Remember, we have to work backwards. So I am saying 4 divided by 8 is 1/2. So our rate is 1/2 and our number of terms is 7. So I'm taking this information right here and I'm plugging it into the sum to get my answer. Okay? All right, it says express this geometric series using sigma notation. Okay? Remember, you use this. You may want to flip back to page or to number. Where did we write that at? We wrote that somewhere today. You may have to flip back on the video. Okay, so remember, use the sigma. I want you to try that one on your own. And then C, all you're doing is expanding. Okay, so try B and C. Okay, if you have questions, email me. I'll be glad to help. Here in a little bit, I'm going to go through the more practice and help you get started on that. That way, if you have questions, you can ask me on that as well. Hope everybody has a good day. Don't forget your student activity sheet 2 about arithmetic is due today at 3 p.m. You must go through all of Agile Mind. There are 2 questions on there for you to get full credit. The one that I'm videoing now is due tomorrow at 3 p.m. Okay, more practice, and your quiz is due Sunday at 6 p.m. The quiz opens tomorrow morning. So if you have questions, let me know.